Right now, there is a machine flying through space that is older than most of the people watching this video, running on computer chips less powerful than a musical greeting card. And it just spent 5 months in 2024 sending NASA nothing but gibberish. Engineers on Earth had to debug it from 15 billion miles away, using a communication link so slow that every message took nearly 2 days to get a reply. They fixed it. And what that machine has been quietly telling us since then is forcing physicists to rewrite what they thought they understood about the space just outside our solar system. This is Voyager 1, and the strangest part of its story isn't the distance, it's what it found when it got there. Let's start with why it was built at all, because the popular version of this story usually gets the emphasis wrong. In the mid-1960s, a graduate student at NASA's Jet Propulsion Laboratory named Gary Flandreau was doing what sounds like a fairly dull assignment, calculating the future positions of the outer planets for a research paper. What he noticed almost by accident was that Jupiter, Saturn, Uranus, and Neptune were about to line up on the same side of the Sun in a way that happens only once every 176 years. A spacecraft launched in the late 1970s could use each planet's gravity as a slingshot, stealing a bit of each planet's orbital momentum to gain speed and bend its own path toward the next target, all without burning extra fuel. Done right, a single mission could visit all 4 outer planets. Miss that window, and the next one wouldn't open until the 250s. That single orbital coincidence is the real reason Voyager exists, not curiosity in the abstract, a closing door that only opens once every couple of centuries. NASA's original ambition, informally called the Grand Tour, would have used 4 separate specialized spacecraft to hit every planet with dedicated instruments. Budget cuts in the early 1970s killed that version. What survived was a scaled-down compromise. 2 general-purpose spacecraft, built using leftover Mariner program spacecraft designs to save money, and given the less grandiose name Voyager. Even in its reduced form, it was an enormous gamble. Each Voyager probe had to survive nearly a decade in space, endure the radiation belts around Jupiter that are strong enough to fry unshielded electronics, and keep functioning across distances no spacecraft had traveled before. Voyager 2 launched first, on August 20th, 1977. Voyager 1 launched 16 days later, on September 5th, but on a faster, more direct trajectory that let it arrive at Jupiter first and overtake its own twin in deep space, which is part of why the numbering feels backwards to a lot of people encountering this story for the first time. Now here's the part everyone remembers: the golden record. Carl Sagan at Cornell University led a small committee tasked with putting together a physical message in case either spacecraft was ever found by another civilization, however unlikely that might be. The record itself is a gold-plated copper disc, designed to last 1 billion years in the vacuum of space, containing greetings in 55 languages, a range of natural sounds from Earth like wind, thunder, and whale calls, and 90 minutes of music curated from wildly different cultures and eras, everything from Bach and Mozart to Chuck Berry's Johnny B. Good. The selection process wasn't smooth. There were arguments over which tracks represented humanity fairly, concerns about licensing, and last-minute additions right before the record had to be finalized for launch. One of the more human footnotes in the whole project involves Sagan's creative director, Anne Druyan. 2 days after she and Sagan privately agreed to get married, she went into a lab and had her own brainwaves and heartbeat recorded as part of an hour-long meditation exercise meant to represent human thought and emotion for the record. That data, essentially a snapshot of a woman falling in love, encoded onto a copper disc, is currently somewhere past the edge of our solar system. It's a beautiful story. It's also, I'd argue, not really the point anymore, and we're going to come back to why in a few minutes. Before we get into what Voyager actually discovered out there, if you're finding this interesting so far, this is a good moment to hit subscribe, because we're about to get into the part of the story most people have never heard. The part where the mission stopped being about golden records and started being genuinely strange. So, the Grand Tour happened, and it delivered. Voyager 1 passed Jupiter in March 1979, capturing the first clear evidence of active volcanoes on the moon Io, something nobody had predicted with confidence beforehand. It reached Saturn in November 1980, sending back images sharp enough to reveal that Saturn's rings weren't a handful of broad, simple bands, but thousands of narrow ringlets, some of them braided in ways that didn't match existing models of how ring systems should behave. Mission accomplished, technically. NASA could have called it done right there. Instead, Voyager 1 kept going, and this is where the story most people know ends, and where the story most people should know actually begins. For 3 more decades, Voyager 1 climbed outward through the solar system's outer reaches, a region called the heliosphere. Think of it as a bubble. The sun doesn't just emit light, it constantly emits a stream of charged particles called the solar wind, and that wind inflates a rough bubble around the entire solar system, pushing back against the thin soup of gas and radiation that fills the space between stars. Voyager 1 spent years crossing the outer skin of that bubble, a turbulent zone called the heliosheath, where the solar wind slows down dramatically and gets choppy, like water piling up against a slower current downstream. On December 16, 2004, at a distance of about 94 astronomical units from the Sun, Voyager 1 crossed what's called the termination shock, the point where the solar wind abruptly drops from supersonic to subsonic speeds. NASA scientists at the time genuinely expected the true edge of the bubble, the heliopause, to be reasonably close by, maybe just a few more years of travel. It took another 8 years to get there, and even figuring out exactly when it happened turned into its own small scientific mystery. Here's why. There's no wall in space, no sign that says you are now leaving the solar system. The heliopause is defined by pressure, the exact point where the outward push of the solar wind finally equals the inward push of the interstellar medium beyond it. You can't see that boundary with a camera. You have to infer it from instrument readings, ideally by directly measuring the density and temperature of the particles around the spacecraft. And Voyager 1's most useful instrument for that exact job, its plasma spectrometer, had actually stopped working back in 1980, damaged during the Saturn flyby. For over 3 decades, the spacecraft had been flying essentially blind to the one measurement it would eventually need most to prove it had left home. So how did anyone figure out when it crossed over? In April 2013, a solar eruption from the Sun sent a shock wave rippling outward through space. 11 months later, that wave reached Voyager 1, over 12 billion miles from home, and made the surrounding plasma vibrate like a struck bell. Voyager's plasma wave instrument, which was still functioning even though the spectrometer wasn't, picked up those vibrations, and the frequency of that vibration directly reveals how dense the surrounding particles are. Don Gurnett at the University of Iowa and his team ran the numbers and got a shock of their own. The electron density around the spacecraft had jumped roughly 40 times higher than anything measured back in the heliosheath. That density number was consistent with interstellar space, not the solar wind. Gurnett's team published the finding in the journal Science in September 2013, and NASA made the announcement that Voyager 1 had actually left the solar system's bubble months earlier, back on August 25, 2012, without anyone knowing it in real time. The spacecraft had crossed one of the most significant boundaries in the history of exploration, and it took an accidental solar flare and nearly a year of data analysis just to confirm it had happened. For a while, some researchers pushed back on the date entirely, arguing the data was ambiguous. It wasn't until Voyager 2, following a different path through the heliosphere, independently crossed its own version of the same boundary in November 2018, with a working plasma instrument this time, that scientists got a clean, direct confirmation of what Voyager 1's indirect measurements had suggested 6 years earlier. 2 spacecraft, 2 different exit points, and finally, real agreement on what interstellar space actually looks like from up close. That alone is a strange enough story. But it's not the part that actually rattled physicists. Here's what did. When Voyager 1 crossed into interstellar space, researchers expected the direction of the surrounding magnetic field to shift noticeably. Inside the heliosphere, the magnetic field is shaped by the sun's rotation and the solar wind. Outside it, in true interstellar space, the field should be shaped by entirely different, far older sources, remnants of other stars, past supernovae, the ambient structure of the galaxy itself. A change in origin should logically produce a change in direction. It didn't change, not by much. Leonard Berlaga's team at NASA's Goddard Space Flight Center found that while the intensity of the magnetic field jumped as expected once Voyager crossed over, its orientation barely moved. The interstellar magnetic field right outside our solar system's boundary was, for reasons still not fully explained, aligned almost in step with our own solar system's field. That single result complicated the tidy mental image scientists had been working with, a clean seal between 2 separate, independent magnetic systems. Instead, the heliopause behaves less like a sealed door and more like a permeable membrane, one where the sun's magnetic influence doesn't fully let go even after you've left the bubble of particles behind. Some researchers have proposed that our sun's magnetic field is somehow physically connected, or draped, into the surrounding interstellar field in ways that current models don't fully capture. Nobody has a complete explanation yet. Then, in 2021, came a discovery that genuinely surprised the people running the mission. A Cornell graduate student named Stella Ocker was combing through years of Voyager 1's plasma wave data and noticed something nobody had specifically been looking for: a faint, continuous hum. Not the occasional dramatic spike from a solar shockwave arriving months or years apart, which is how scientists had been getting most of their density readings up to that point. A persistent, low-level oscillation in the plasma, present essentially all the time, quietly humming along in the background. Published in Nature Astronomy in 2021, Ocker's finding meant that for the first time, scientists could measure the density of interstellar plasma continuously along Voyager's path, rather than waiting years between rare solar events to get a single data point. Interstellar space, it turned out, isn't the near-perfect silence everyone had assumed. It's faintly, constantly ringing, and nobody had the tools to hear it until a machine built in the 1970s happened to be sitting there long enough to pick it up. And here's where I'll push back a little on how this story usually gets told. Most retellings of Voyager treat the golden record as the emotional center of the entire mission, humanity's letter in a bottle, cast into the dark, waiting patiently for someone to find it. It's a lovely idea, and Sagan clearly meant it as a genuine statement about who we are as a species. But realistically, the odds of that record ever being intercepted by anything are close enough to zero that it functions more as art and symbolism than as science. What Voyager is actually doing, right now, is far less poetic and far more remarkable in a way that gets undersold. A machine built with less computing power than a modern digital watch is still returning usable, peer-reviewed data that is actively revising physics models of the boundary of our solar system nearly half a century after launch. The message in a bottle was symbolic, and it'll probably drift forever unread. The science is real, ongoing, and still surprising people who've spent entire careers studying exactly this region of space. Which brings us to the part of this story that almost ended everything. Voyager 1 runs on a radioisotope thermoelectric generator, a device that converts heat from the natural decay of plutonium-238 into usable electricity. There's no solar power option this far from the sun. The sunlight is far too weak by this distance to do anything useful. At launch, the generator produced about 470 watts, roughly enough to run a couple of hallway lights. Nearly 50 years later, that output has dropped dramatically, losing around 4 watts of usable power every single year, permanently, with absolutely no way to refuel or recharge it. Ever since the early 2000s, NASA's engineers have been making increasingly difficult choices, shutting down instruments one at a time in a specific order, prioritizing the ones still returning the most valuable science, just to keep the spacecraft's essential systems, and its ability to communicate at all, alive for as long as possible. The camera system was shut off back in 1990, shortly after taking the famous pale blue dot photograph of Earth from billions of miles away. Various heaters and secondary instruments have been switched off gradually since then, each decision permanently narrowing what the spacecraft is still capable of doing. Then, in November 2023, Voyager 1 stopped making sense entirely. It kept transmitting a signal on schedule, but the data packed inside that signal was garbled, a repeating pattern with no usable information buried in it at all. For nearly 5 months, the spacecraft that had survived flybys, radiation belts, and 46 years of continuous deep space operation was effectively speaking gibberish, and nobody on the ground knew exactly why. The team, led by JPL project manager Suzanne Dodd, spent months methodically working through the problem with the tools available, which were extremely limited given the distance involved. Eventually, they traced the fault to a single corrupted chip inside Voyager 1's flight data subsystem, the onboard computer responsible for packaging science and engineering data before it gets transmitted back to Earth. That one chip held about 3% of the system's total memory, and it had simply failed after decades of continuous operation and cumulative radiation exposure. You cannot send a repair technician 15 billion miles. You cannot even have a real-time conversation with the spacecraft, since a radio signal takes over 22 hours to arrive one way, and another 22 hours for any reply to come back, meaning every single test cycle burns almost 2 full days. What the team did instead was carefully rewrite the affected code and relocate the working pieces into other, still functional sections of the computer's memory, essentially performing live surgery on a spacecraft's 1970s-era operating system from nearly a full light day away, verifying every single change across a round-trip communication delay of roughly 45 hours before moving to the next step. By April 2024, Voyager 1 was talking sense again, sending back clear engineering data for the first time in almost half a year. That is not a footnote. That is one of the more quietly astonishing engineering achievements in the history of spaceflight, and it barely made the news outside space circles, overshadowed by newer, flashier missions. But the power problem doesn't go away. It only gets worse year after year with no way to reverse it. NASA has already permanently shut off several of Voyager 1's remaining science instruments to conserve what little electricity is left, and current projections suggest the last operating instruments will need to be switched off sometime around the middle of this decade. Even after that point, the spacecraft could likely still transmit a basic engineering signal for a while longer, confirming it's alive without sending back any actual science. Most estimates put the point of total, final silence somewhere in the early 2030s. Plausibly between 2030 and 2036, when the power output finally drops below whatever minimum is needed to run even the transmitter itself. After that, Voyager 1 doesn't stop moving. It just stops talking. The spacecraft will keep drifting outward, silently, indefinitely, carrying the golden record through a vacuum with almost nothing around to erode it or slow it down. NASA's own long-range projections put its closest approach to another star, a dim red dwarf called Gliese 445, at around 40,000 years from now. And even then, closest approach only means passing roughly 1.6 light-years away. It's not visiting that star in any meaningful sense. It's barely brushing past it, on a journey with no real destination that will likely outlast our species, our civilization, and quite possibly the sun itself. So here's where I land on this story. Voyager 1 was sent out as a symbolic gesture and a scientific tool. In that order, at least according to how it's usually framed by documentaries and headlines. I think the actual history runs in the reverse direction. The record is a beautiful piece of 1970s optimism that will almost certainly drift forever without ever being found by anyone or anything. The real legacy is a machine, built by people working with slide rules and computing power a tiny fraction of what's in your pocket right now, that is still expanding human knowledge about the edge of our own solar system nearly half a century later, one faint, dying signal at a time. It has already outlived its own design specifications by decades. It has already survived a failure that should have ended the mission for good, and it's still teaching us things about interstellar space that nobody predicted before it got there. We built something that outlived its own expiration date so thoroughly that the engineers who designed it never expected to still be fixing it in their retirement. And in a few short years, it's going to go quiet forever, mid-sentence, somewhere past the edge of everything we've ever directly measured. What do you think NASA should prioritize with the time Voyager 1 has left, squeezing out the last bit of science data, or preserving power for as long a basic signal as possible, just to say it's still out there? Let me know in the comments.